Our homework that we had over the weekend was on the concept of work, of course, which we defined as the change in energy. We have to go over two questions here, questions number 4 and 5 from the worksheet that we had on work. Number 4 says a 1.3 times 10 to the 3 kilogram car begins at rest and accelerates to a speed of 60 kilometers per hour over a distance of 200 meters. How much work is done on the car? Well, work is defined as the change in energy, and that little tidbit is on your data sheet. But in addition to that definition of work, really, W is equal to delta E, we have this equation on our data sheet. W is equal to F times D times cosine theta. A couple quick little questions first before we actually apply one or both of those to answer this question. First of all, is work a vector or a scalar? Is work a vector or is it a scalar? Really? It's a scalar. Energy is a scalar. Work is going to be a scalar as well. What are the units that we use for work? Joules, yeah, good. If energy is measured in joules, then the change in energy is going to be measured in joules as well. What's the whole idea with the theta in there, the cosine theta? Sometimes you see the equation written as F times D. Sometimes you see it written as FD cos theta. What does theta stand for? Don't just say, oh, it's an angle. Like, what angle are we talking about here? It's the angle between the way that the object is pushed and the way that the object moves. If we happen to push it that way and it moves that way, what's the angle going to be? Natalie, what's the angle going to be between the way that I push it and the way that it moves it if I push it this way and it moves this way? 0. And cos 0 is 1. So that whole cosine theta disappears, right? If I push it this way and it moves this way, how can I push it this way and it moves this way? Well, maybe it was moving this way already, and I'm pushing it this way by friction to slow it down. Then we're going to say the angle is 180. Cos 180 is -1. We get a negative value for work, and it just tells us that we've lost energy in that case, right? We still get to drop the cos theta. 9 times out of 10, we do get to drop the cos theta because when we push it in a certain direction, it moves in that same direction. In this case, we get to drop the cos theta. Question number 4, we get to drop the cos theta because presumably if the car is beginning at rest, accelerates to 60 kilometers per hour along the road, parallel to the road surface, then presumably it's being pushed parallel to the road surface. So the angle would be 0, cos theta would be 1, and the equation would become F times D. Now, what do we got? What do we have in this question? We know that the mass of the car is 1.30 times 10 to the 3 kilograms. We know that the displacement is 200 meters. We know that the work is what we're looking for. What else do we have here? Tell me what other givens that we have here. Clearly, there is at least one other given here. Devin, what else we got in this question here besides M, delta D, and W? So VF is 60 kilometers per hour. You're right. We got to convert that to meters per second. Let's circle that in red, actually, just to remind us of that. Is there anything else we have if we kind of read between the lines here? Mouse? VI is what? Good. VI is 0 meters per second. Let's convert this kilometers per hour to meters per second here now, okay? 60 kilometers per hour. We got to convert the kilometers to meters first. What's the conversion factor, William? Kilometers to meters. Good. So it's going to be 60 times 1,000. Gives me 60,000 meters per hour. And then, Taylor, what's the conversion factor from hours to seconds? 3,600. So we're going to say 1 hour is 3,600 seconds. 60,000 divided by 3,600 gives me what, Nick, for the speed there? 16.666. Yeah, let's use the unrounded number to 3 or 4 decimal places. Okay. Probably not going to make a difference there, but just in case. Good, Nick. So now we're going to find the work done. We've got a couple of options here, right? It's work is equal to delta E and work is equal to F times D. What do you want to try here? F times D or work is equal to delta E? They're both valid. If you can make one of them work, it's good. If you can make both of them work, it's good. It doesn't matter which one you use if you can make them both work. Which one do you want to try? Which one do you want to try there, Reese? Okay, just like back when we were doing our group A, group B equations, if we had a group B problem and we tried the wrong equation, it was okay, right? There was nothing wrong with picking the wrong acceleration equation. Here we got two things that are equal to work. Pick one of them. If it doesn't work for you, pick the other one. Neither one of them will lead you to the wrong answer. So the suggestion here was to try F times D. But I got a problem. I don't know what F is, right? You have a suggestion for that? Okay, so we can say F is equal to M times A, but I got a problem. I don't know what A is. Suggestion? Do I have to abandon this? Ben, do I have to abandon this? Or can I keep going and still somehow find it? How am I gonna keep going though? How am I gonna find A? Sorry? Am I going to find A? You said I'm going to keep going with this strategy and not try something else. So how am I going to keep going? How am I going to find the value of A there? Okay. How am I going to find the value of A there, David? Listen, look at what you got, guys. Look at the variables that you have here, and look at what you're looking for. I mean, ultimately, we're looking for W, right? But if we're going to use this technique that Reese suggested here, W is equal to F times D, and F is equal to M times A, then we've got to find the value of A somehow. We're going to go back to our group B equations. We're going to pick an equation from our group B equations to find the value of A. What do you suggest that I do, Julia? Okay, we'll come back to that. I think I know what it is. Okay, honestly, that's the way I think. It's going to be the way that I would have done this question, but this also works. We just need the value of A here. Cameron, how are you going to find the value of A? Okay, Emma? Okay, good. Now, I'm not going to go through this process of finding the value of A, then finding the value of F, and then finding the value of W, but you can see how it could work, right? We have all the variables in here except for A. Solve for A, get its value, plug it back into here, multiply it by mass, get the value for force, get its value, plug it into here, multiply it by the displacement, and lo and behold, we're going to get the work done. Now, Julia, it was Julia, right? Yes. That said that you had another way of doing it. Julia, what did you do? Okay, that's what I would have done as well. But this is just as good. Okay, the method that whoever it was that suggested that, I think it was you, right? Yeah, that's just as good. It's just a tiny bit more work, that's all. It's just as correct though. So Julia and myself both said basically W is equal to delta E, the change in energy. Now we look at what the final energy is. It's kinetic, right? The car's at rest and then it's moving. So the final energy is kinetic. EF minus EI, we got kinetic energy as the final energy. What kind do we have at the beginning when the car's at rest on the ground? No. It's at rest. So just because it's at rest doesn't mean it has potential, remember, okay? It's got to have a height to have potential. And it doesn't have, it's not moving, no kinetic, it doesn't have a height, so there's no potential. So the change in energy is simply equal to the kinetic energy that it ends with minus 0. So all we're going to do here is say 1/2 of mvf squared. So we're going to say 1/2 of 1300 times 16.6667 squared. And when we do that, we should end up getting 1.81 times 10 to the 5. Did anybody do it the other way, Reese's way, W is to go to F times D, and actually get a final answer? All right, let's take a look at the last one here, number 5. A 1,300 kilogram car begins at rest and accelerates to a speed of 60 kilometers per hour over a distance of 200 meters. What's the net force acting on the car? This question sounds an awful lot like the last question, except that I don't see the word work in there. Right? We're starting off with a car in question number 4. Cars at rest accelerates to a certain speed over a certain distance. Question number 5, start off with a car at rest accelerates to a certain speed over a same distance. In fact, it's the same speed and the same distance in the same car. Just in question number 1, we're looking for the work done. And in question number 2, we're looking for the net force that acts on the car. So a couple of options here. If you do it Reese's way, which question number 4, that is, Reese's way, using W is equal to F times D, then Reese would already have the value of the force, right? And he could just say, oh, I got it in the last question. Plug it in. What was it, by the way? Yeah. Okay, fair enough. But no, that's okay. So Reese just subbed in equations and did a couple things in his calculator, so he doesn't actually have that in-term value of force. Okay, that's okay. If he did, then he has the value for the force for number 5 already, right? Because everything else is the same. Now, if you didn't do it Reese's way, the W is equal to F times D way. If you did it my way, or Julia's way, whoever you want to give credit to, W is equal to delta E equals 1 half mv squared, then we've got to find it some other way. Well, look at what we just found a minute ago. Julia, we found the work in question number 4, right? 1.81 times 10 to the 5 joules. We know the displacement is 200 meters. So we can find the force there, right? Now, if question number 5 was different than question number 4 with different data, well, then we could go and find the work in question number 5 the same way as we did in question number 4, and then plug it in and solve for F that way. Or you could do it Reese's way. Say W is equal to F times D right from the start, find the force by using M times A, and find the acceleration by using VF squared is equal to VI squared plus 2AD. When you do this, by the way, force works out to be 903 newtons. Regardless of whether you do it Julia's way, using W is equal to delta E and then F times D in question number 5, or whether you do it Reese's way, using F times D right away and finding force using M times A, using VF squared is equal to VI squared plus 2AD. How many people did number 5 like this? We had the work, set it equal to F times D. Emma? Yeah? How many people said question number 5, oh, look, I can, F equals MA, A equals VF squared is equal to VI squared, so on? You guys did it that way? For the force? I got 903, but it could be a rounding issue there. Anybody else get 905? 903? So it might have been you that had the rounding issue there. Take a peek at it, and then if you can't get 903, just let me know and I'll help you out with it. Okay? So which way is a better way? Which way is a better way? This way, saying F is equal to M times A, or that way, saying W is equal to F times D, knowing the value of W? No way is a better way, right? They're both right. If they're both right, then they're both good ways. Whichever way works for you is the way that you should end up doing it. All right. Let's do, since we had a little bit of trouble with that question, let's take a look at one more question here. So as a 1,200 kilogram car accelerates from rest to 90 kilometers per hour over a distance of 200 meters, what's the work required to do this, and what's the net force required to do this? You know what, I'll give you guys a few minutes to work on that one at your desks, and then we'll take a look at it as a group once you've had a chance to do that. Okay, let's have a peek up here, whether we're finished or not, okay? The question says a 1,200 kilogram car accelerates from rest to 90 kilometers per hour over a distance of 200 meters. What's the work required to do this? What's the net force required to do this? All right. Looking for work here. We know that work is equal to delta E. We know that work is equal to F times D. It's F times D times cosine theta, but presumably here we're pushing it in the same direction that it's actually moving. So we're going to say F times D. What do you want to use here? Delta E or F times D? What do we want to use here? Let's say, Alana, what do you want to use here? Delta E, okay. Let's circle that. Let's write down some givens now before we start using that equation here. M is equal to 1,200 kilograms. VI is 0 meters per second. VF is 90 kilometers per hour, which we're going to have to convert to meters per second, which is 90,000 meters. The time here, or the hours, is 3,600 seconds. That gives me 25 meters per second VF. And my displacement is 200 meters. I'm looking for work, and I'm looking for the force that's required to do this. Remember, there's two ways. Okay, Alana suggested that we use delta E for work, which is final minus initial, which is kinetic, in this case, minus 0, which ends up being equal to 1/2 of 1,200 times 25 squared. That one gets 375,000 joules. Agree with that? I'm going to round that to 3.8 times 10 to the 5 joules, but that one's got my unrounded number. I want to keep that unrounded number because I'm going to use that in part B of this question, right? So final answer for part A is 3.8, but I'm going to use the unrounded number for part B of the question. Now I want to find force. W is equal to F times D. F is equal to W over D. W is 375,000 joules divided by 200 meters. Dylan, what'd you get for that one? 1,875, so 1.9 times 10 to the 3 newtons. Okay, how many people did it the other way? Said W is equal to F times D, found F using M times A, VF squared is equal to VI squared plus 2AD. Who did it that way? Okay, and what'd you get? Same thing. Okay, go figure. Unless you or I or Dylan makes a silly mistake, we have to get the same answer, right? Good. All right, I'm going to give you some questions to work on for a few minutes here. It's page 305, some check and reflect questions. You're going to do question number 1 to 10, except for number 8. So it's 1 to 7 and 9 to 10. We're not going to give you the rest of the class by any means to do these questions, but we'll give you probably close to 10 minutes to work on those questions. Give you a head start on it.